These last examples can lead us to some conclusions about the end behavior and asymptotes of rational functions. Now keep in mind, rational functions by definition mean that we're going to have a polynomial divided by a polynomial. This isn't going to be, let's say, a transcendental function divided by a polynomial, or a or transcendental function divided by a transcendental function. So transcendental functions are the trigonometric functions, logarithmic functions, exponential functions, those ones. So it's not going to be any of those. So as long as it's a polynomial divided by a polynomial, then we've learned some characteristics without perhaps even realizing it. So for example, if the degree, that's what DEG stands for, the degree, if the degree of the numerator is less than the degree of the denominator, then y equals 0 will be a horizontal asymptote. And we saw that right here in example 3a. The degree of the numerator was 1, because that's to the 1 power. The degree of the denominator was 4, that's to the 4th power. Since that denominator degree is larger than that numerator degree, our horizontal asymptotes indeed ended up being 0. So this would be example 3a. That was the example we saw that was like this, where f of x was equal to 2x plus 1 divided by 3x to the 4th plus 2. So the horizontal asymptote was y equals 0. Now, if the degree of the numerator is greater than the degree of the denominator, which we actually saw in example 3c right here, the degree of the numerator, it was 3, that's x cubed right there. The degree of the denominator was 1. When that happened, you see that we had no horizontal asymptotes. So this would be example . So no horizontal asymptotes. We were not heading to any number in particular as we let x go to infinity or x go to negative infinity. All right, now what about the degree of the numerator equals to the degree of the denominator? Well, we saw that as well. We saw that in example 3b right here. Degree of the numerator was 2, right? It's because it's x squared. Degree of the denominator was 2 because it's x squared. So then it became a ratio of their coefficients. This has a coefficient of 3. This has a coefficient of 1. 3 divided by 1 makes 3. And that was our horizontal asymptote. Now, using this little end behavior chart does not count as analytical work, but it does help us kind of just know how this works. So it was 3x squared minus 7 over 1x squared plus 5x. So the horizontal asymptote is y equals 3 divided by 1, right? Or just y equals 3. All right, again, just using this little trick doesn't count as analytical work. Matter of fact, I'm going to make a note of that down here. So this table does not, this table tells us how end behavior is, or how an end behavior works, but it does not count as analytical work for the sake of, exams or something like that. There we go. Oops, sorry, that was a little off screen. Okay, so now that we know about the horizontal asymptotes and we've kind of tied that together, we do want to just mention about the slant or oblique asymptotes and the vertical asymptotes, which this is a little out of order, but let's do vertical asymptotes first because we already know how those work. So vertical asymptotes are when the numerator and denominator have been reduced and simplified, and they share no factors. That's what a lot of students forget. So in other words, you must simplify first. Simplify first. Then any values that cause the denominator to be equal to 0, but not the numerator. Let me just mention that. Are vertical asymptotes values. Now, of course, if it simplifies, then it shouldn't have happened with the numerator anyway, but just to be clear, why is that the case, not the numerator part? So let me just write another note, just a little reminder yet again, that 0 over 0 and infinity over infinity are indeterminate forms. So at this stage, the only option you have is to simplify first, right? It's indeterminate forms. Simplify first, and if simplifying leads to nowhere, then you're done. At least in this course. There are things you can do, but not in this class. So first, if it leads nowhere, right, if you don't get out of the 0 over 0 thing, then the limit does not exist. Right? So if you have an indeterminate form, well, first of all, let's back up. You first simplify, right? Factor, cancel, use your tricks of your trade, etc. All the pre-calculus tricks that you know, right? So using all your pre-calc tricks, quite frankly, most of the time it's just factoring and canceling. But, you use all that stuff, and if you can't get anything good out of it, you simplify first, pre-calc tricks, and then any values that would cause the denominator to be equal to 0, but not the numerator, are vertical asymptotes. Sorry, my Steam account just showed up there. All right, so then just a little reminder that 0 over 0, infinity over infinity are indeterminate forms. They don't give us an answer. So we try to simplify just like we're doing up here. And if it doesn't go anywhere, if we still get 0 over 0 and infinity over infinity, then we're just going to say it doesn't exist for now. There are other options, but they would take, well, knowing calculus, knowing chapters 3 and 4 to do. So for our purposes, we're going to be done. All right, now I skipped over the slant asymptote bit, so let's go back and look at the slant asymptote. So the slant asymptote happens when the degree of the numerator is 1 greater than the degree of the denominator, right here. So it can only be 1 more than, no more, no less. So when that happens, let me give you an example. As a matter of fact, we have an example, and it's right below. I think for your notes it'll be example 4, but for me it's going to be example 5 because I'm going to renumber these examples, but there you go. It's this one. There will be a slant asymptote here because the degree of the numerator is 1 greater than the degree of the denominator. So for me it's 5 currently, but for you watching it might be example 4, so check your notes. But it'd be f of x equals x squared over 2x plus 1. That's going to have a slant asymptote, because the degree of the numerator is 2 and the degree of the denominator is 1, and that is a difference of 1. All right, so actually that's our next mission, is to find those asymptotes. So let's go do that example real quickly. All right, so let's identify the asymptotes of this function. So we know it's going to have a slant asymptote, and since it's going to have a slant asymptote, it's not going to have a horizontal asymptote. As a matter of fact, I can make a little note right here. It has a slant asymptote. If it has a slant, the degree of the numerator is greater than the degree of the denominator, which, if you remember, right up here has no horizontal asymptote. So if it has a slant asymptote, it cannot have a horizontal, and vice versa. I'll make a note of that. There, I just added that little note into that page. So if a function, FCN, if a function has a slant asymptote, it cannot have a horizontal asymptote, and vice versa. Just adding a little asymptote right here. Right. So if it has a horizontal, it can't have a slant. If it has a slant, it can't have a horizontal. Done. So when we look at our example, our next example, it's going to have a slant asymptote because we can tell because the degree of the numerator is 1 larger than the degree of the denominator. So I know I'm going to have a slant asymptote, and I also know I'm going to have a vertical asymptote. So let's find the vertical asymptote first, because the vertical asymptote should be relatively easy as long as I don't mess up like I did on the last problem. Sorry, my letter got weird there. Okay, so 2x plus 1 would be equal to 0. this is already simplified, so I don't need to worry about simplifying. Subtract 1, 2x equals negative 1, x equals negative 1/2. So my vertical asymptote is right there. Vertical asymptote, VA. Done. All right, now the slant asymptote. Well, that's going to be not so much fun. So, well, I mean, I'm going to enjoy it, but I don't know if you will. So the slant asymptote, in order to find it, you actually have to do polynomial long division. Oh, let me make just a real quick note here. Horizontal asymptote, I'm going to say none. All right, slant asymptote, because degree of the numerator is 2, and the degree of denominator is 1. Right? So 1 power and 2 power. So I know there will be 1. And the way to find that is polynomial long division. And that's also how I know there's no horizontal. Right? All right. Okay, so polynomial long division. Let's see how much we remember. So you have to take the numerator and you put it inside the division box. So I don't know what your teachers called it, but I was learned that it was like the division house. So it goes in here, x squared. And then I have no x term and I have no constant term. So I'm going to put plus 0x plus 0. And over here, I'm going to put my denominator. So then I want to look at this and I think to myself, okay, I need 2x to multiply by something that'll turn it into x squared. Well, rather obviously that something's going to have an x, because x times x will get me x squared, which is great. But if I just do x, I would get 2x squared, which is no good to me. I need just regular x squared. So if I use a half times 2 makes 1, and sure enough, then it is the same. But of course, I can't just multiply a half x times 2x. I have to multiply a half x by both of these terms. So a half x times 2x makes 1x squared. A half x times 1 makes plus a half x. Now we subtract that whole thing. So we subtract x squared, take away x squared, makes 0, which is what we wanted. That was our goal. So good. 0x, take away a half x, makes negative 1/2 x. Now I bring the 0 down for the constant term, and then I do it again. So I need to multiply 2x by something to get me negative a half x. Well, it's not going to have any x in it, which is good because I've already used up my x term. But it's not going to have an x in it because x times 2x would get me x squared. So it's just going to be a number. So I need to multiply by a number to get from 2 to negative a half. We'll start with negative 1, right? So if you multiply by negative 1, that would be negative 1 times 2, which is negative 2. So I've got the negative part, but I don't have the fraction part. If I do negative 1 over 2, that would be negative a half times 2, that would be negative 1, so that's no good. But if I go negative 1/4, see what I did there? A fourth times 2 is a half, and it works. And a negative fourth times 1 makes negative a fourth. And then I subtract the whole thing. Negative a half minus a minus is negative a half plus a half. So these two are like terms, they combine and they make nothing. So this is gone, which was your goal, by the way. Right? And then you have a remainder right here of 0 minus a fourth, which is 0 plus a fourth. However, we can disregard that. The remainder does not matter for the sake of the slant asymptote. The slant asymptote is actually this bit right up here. So let me make a little note right here. Disregard. Remainder. Disregard. I can spell the remainder. And this right up here will get you your slant asymptote. Your slant asymptote, or oblique asymptote, whichever way your instructor taught you in pre-calculus, would be y equals 1/2 x take away 1/4. There is my slant asymptote. And just to prove to you that this is true, I've of course graphed it in Desmos. And you can see right here the graph, and there is the slant asymptote right there, and there's the vertical asymptote right there. And there's the function. So I'll copy that onto my piece of paper. And then there it should be. And of course I've labeled it and given it scale and everything. It's not a perfect graph, but it shows the asymptotes just like they should be shown.